stereo effect, amazing. So quick note, I will be presenting the same results that my team members were presenting at DataFest. So in case any of you attended the DataFest session, it's a good time to switch to one of the other tracks, okay? Okay, so I will be talking about the goal that we're pursuing in our group at Samsung, and many of our groups are, group members are in one way or another affiliated with Skoltech, including myself. Let me start by just showing the group of okay, let's try.
Mine was working.
I think I just took two results. No, that way. No, can I maybe try this one? Okay. Sorry about that. Ну, включен. Okay, I think it was just frozen, the computer. Okay, let me start by showing the group of people who has actually achieved the results that I will be presenting. It's nice to see some of them here. Okay, so I will start by discussing what is this goal of telepresence, why does it matter, why is it worth pursuing, and then decompose it into some sub-problems and then discuss our recent advances on these sub-problems. Let me start with a brief history of telepresence. By telepresence, I mean the ability of people to converse, to discuss things, to communicate across distances. If you take it as broadly, then the first telepresence technology was nothing else but writing, okay? And it's quite an old technology with a very profound influence on humanity. Writing was the first one. The next big milestone came much later in the 19th century with the advance of telegraph. Telegraph has added the ability to communicate in real time. The bandwidth was very low, but it was like, again, it shrank the world, it changes the history of the world, it changes the people's lives and how people perceive the world a lot. Then the next big advance is phone. It's like large bandwidth, voice-based, real-time telepresence. And again, the way our life is shaped by the presence of phones is very substantial. Okay. And maybe this is the state of the art of what we have today. Of course, like research labs and have different prototypes which are more advanced than this, but for consumers, for just mortals, this is the best you can get. You get Skype or similar video conferencing. And it's amazing. It's completely, for a person, say 50 years ago, 100 years ago, this is completely science fiction, but it has its limitation, okay? So what you see on the screen is something flat, 2D, it's fixed viewpoint. You can change your viewpoint, but the image will not change. And it's also limited to just the face, basically because your field of view is limited. So where are we going? Let's check with science fiction and Hollywood. This is something we want to get to. 3D, meaning that the image changes as I move around. Full body, free viewpoint, very high resolution, very high frame rate, maximum realism, although not from this illustration that realism may mean different things. For example, this guy is blue. Maybe in real life this guy, you would imagine, would not be blue, but people don't mind him being blue, being unrealistic in this way. But somehow it's perceived as, looking at this, we have like a very strong feeling of what this person is doing in reality, and we trust this, we perceive as if this person being in the, right here, okay? So this is like a lesson that realism may mean different things, and some artifacts, some inconsistencies of reproduction are better than others. Okay, but so this is where we're going. Of course, we're not yet there. What is good, though, is that the hardware, the display technology, is improving massively over the recent years. Even like if you look like 10 years back, now we have consumer VR. We're now about to start having consuming AR glasses. Screens have improved immensely over the last 20 years. Now we can have like a big screen which occupies a big part of your visual field rather inexpensively compared to what it was used to be 20 years ago. So the hardware is here, the software is not yet here, and this is what we're trying to improve. Of course, we're not alone. Lots of groups around the world are building better software for telepresence. Now let us look at the software side of the things. We can roughly decompose the task into 3 parts. And the first part will be performance capture. So somewhere in the world outside of this room, some person does something and want to capture what she or he does. And we can use various sensors. Here I draw RGB cameras, color cameras, but they not necessarily need to be color cameras. It could be depth cameras, it could be inertial sensors on the body, can be anything. And this is like part of the research plan, is to investigate different sensors. Okay, but we want like contradictory thing from this setup. We want simplicity and compactness of this setup so that you walk into this room, you press a button, and it's working, and your room is not, doesn't look like a workshop, it looks like a normal room. You don't probably want to spend your yearly income on fitting in this room. It should be cheap. We also want completeness and accuracy of what you are doing, right? We want to reproduce this person in full details, then it means that we want to capture all these details. And we're still not in science fiction. We still have limited computing budgets. Our computers are not can compute only so much, so it's also part of the challenge. And all these 3 desires in contradicting each other. For example, we can maybe have a low compute solution, just take a bunch of depth cameras, like tens of them, take the point clouds they generate, combine them and send them. It's a relatively low compute, but it's very non-compact, expensive, and hard to set up thing, right? Okay, then the second part of the equation is like the transmission, and I won't focus on this here. There are lots of interesting problems there, but I assume that it's going to be solved with the advent of 5G technologies and with the improvement of networking. This is becoming less and less of an issue. So we send this scene representation what we have captured to another device, to say this room, and then we need to reproduce this person based on the sent information somewhere here, and we want to be able to reproduce this person from arbitrary viewpoint, so free viewpoint, maybe 2 adjacent viewpoints to render it in stereo. We want highest possible realism, highest possible fidelity, means that it needs to be not only realistic, but also that particular person doing that particular gesticulation, that particular mimics. And again, we want to do it all very cheaply on maybe desktop GPU or maybe even a smartphone, who knows, someday. So we have to work under these constraints. Okay, So today I will instantiate, reduce this setup very general one to a particular variant of it, and the variant will be the following. So we take the person, we actually take one camera, multiple cameras, we extract the 3D body key points, okay, this skeleton, and we send this skeleton, this set of 3D key points, to the remote location. Then we take this 3D skeleton and we render it from a new viewpoint, the one from which we want to obtain the rendering. And we use the avatar trained, pre-recorded for that person, pre-created for this person to render this person. Okay? So this will be our setup. Is it perfect? Is it the right thing to do? Probably no. Probably key points will not capture everything about the person, so it has its limitation. But that's what we'll have today. Okay, and I will first discuss two approaches about avatars and their rendering and their creation, their learning. And this will be most of the time that I will spend today. And then, in the end, if I have time, I will also discuss the left side. How do we capture the key points? How do we capture the avatar, the skeleton? Okay, let me start by discussing the avatar technology once again. This is not a new technology. This has been, avatars have been around for 25 years at least, and they've become, computer graphics people made them very, very realistic. Usually an avatar includes some model of surface geometry, for example, a 3D mesh, maybe some subsurface geometry as well, like muscles, some other objects. And then on top of this geometric modeling, there is also photometric modeling, which usually comes in the form of surface maps, like the texture, the bump map, which redirects the light slightly so that you can get small subtle details, reflectivity maps, all kind of maps, which are usually 2D, and each location in the map associated with some part of the geometry. Okay, and you can do amazingly well, but computer graphics sort of somewhat hit the roadblock, in my view, and in view of computer vision, maybe community. So first of all, creating each new avatar is still very hard in the sense that you need like designers doing their job for days, hours, maybe weeks to create a new avatar of a new person. So it's not that you just take a few photographs and get a photorealistic avatar. You can get like maybe a non-realistic avatar, cartoonish avatar, that's easy, but to get like highly realistic avatar is much, much harder, requires designer labor. And then, especially when this person begins to move, you still hit the uncanny valley. The uncanny valley effect discusses the phenomenon that if your avatar is highly realistic, but you get some things slightly off, then it does seem very creepy to a person. Okay? Somehow our evolution primed us to be very suspicious and very disgusted by a person by an object which looks almost like a person but not quite like a person. So once you start growing the realism, you start maybe with something completely non-realistic like a toy or like a cartoon. It's fine, then you keep it making it better, it's still fine, it's even better perceived. But then once you start approaching the perfect realism, the attitude, the perception, the emotion dips sharply because of this uncanny valley effect, and it's very hard to cross this uncanny valley. And it's actually not trivial even to charter this uncanny valley, in the sense that, once again, some artifacts are okay with human visual systems, some artifacts are not, And it turns out that computer graphics artifacts are not, because they are physically plausible, they're geometrically plausible. So what you see might be a real person, it obeys the laws of physics and geometry, so it almost, you perceive it as this is a real object, but not like a human, and this is the definition of the uncanny valley. So though SIGGRAPH, if you go at SIGGRAPH, you will see amazing demonstrations of those avatars, and still when they're moving, you see they're not perfectly real. Okay. Then the new thing, because of this, in sort of real systems, what companies do when they ship the avatar technology, they make them non-realistic, like these cartoons. Okay, the new trend driven by the advances in neural networks are what we could call convnet people, where the image of a person is synthesized not by traditional computer graphics when you render a mesh and superimpose textures and add lighting, but instead you use generative convolutional neural networks to do the rendering. And initially, like back in 2017, the first system of such kind was synthesizing just the lips, and then those lips were cut and pasted into a pre-existing video. And still it was like a wow effect, and it achieved a very strong realism. And then like later, maybe a year later, it grew to the head and shoulders part, where sort of the system by Kim et al. From Max Planck is that you take an image, you extract the face parameters, you render face using computer graphics tools, and then you put this non-realistic rendering into a convolutional network, and this convolutional network makes it realistic. Adds the background, adds the rest of the head, and it does look, it's not perfect, it still has artifacts, but it's amazingly realistic, at least at the resolution that they have done it. Okay, and then like a year later, about last summer, a bunch of papers came out which tried to do it which successfully did it actually for full body at a limited resolution. This is the system from NVIDIA, this is the system from Berkeley, this is a system from Chinese and Israeli University. And the idea is that you take some body representation like the skeleton, render it somehow, like for example, just indicate where the, render images which indicate where the key points are, put it into a convolutional neural network. And yeah, by the way, I will assume that you know what convolutional neural networks are, roughly. And then generate an image of a person out of this rendering by passing it through convnet. And we started looking at these systems, and they work really well when you reproduce it from the same viewpoint as they were trained for. Here the NVIDIA system has the advantage that they have published the source code, so you can download and play with it. But then when we trained it from a bunch of videos taken from different viewpoints, and then try to see what will happen if we render this person from a new viewpoint, we saw that it's not doing so great. Okay, so our first system was motivated by this disparity between computer graphics, when you have this mesh model and texture, and this new class of methods where you just have a convnet and that's it. So we seek something, we'll try to get best of both worlds and create a hybrid system essentially, which uses textures from classic computer graphics, but it also uses convnets from the new class of methods, and we call it textured neural avatar, and it was presented at last CVPR. So how does it work? Let me briefly go through the architecture. So at test time, the system takes some representation of human pose. For example, rendered key points. This here it's like a beautified version of what the network sees, but essentially it sees the position of the key points in the skeleton projected onto some view. Then a convolutional network takes this stack of maps, this rasterized key point, for example, one channel per each key point, and it takes a bunch of maps, and for each pixel in the image, the network predicts the probability of its assignment to a particular body parts. So we have a dictionary of, say, 25 or so body parts, like the back, the left forearm, the right forearm, the head, and so on. So for each pixel, predict the probability that this pixel belongs to that part. And then the second stack of maps that is predicted are the part coordinates. So for each part coordinates, we predict for each pixel, assuming that it belongs to that part, what are the coordinates on that part system. Okay, and this coordinate system is trained alongside the convolutional network, as we will see. So let's assume for a moment that this coordinate system on each body part exists. For example, that on my front chest there exists some coordinates. It's parameterized somehow, but with two coordinates. So we predict the coordinates in that parameterization. And this kind of representation, body parts plus coordinates, is not our contribution. It has been suggested before us by Facebook AI Labs in that publication. It's called dense posed representation. They have trained a system which takes arbitrary image of a person and predicts this per pixel. We predicted not for an image, but for some key point arrangement. Okay, then given these predictions, we also take a bunch of textures, one texture per body part. So this texture stack is also part of the avatar that we create. And given the body part assignment, given the body part coordinates, and given the textures, we can sort of put the texture onto the image. All this is done by using bilinear sampling, actually trilinear sampling, because we also combine together the body parts according to the predicted weights, and we get an image and we also get a mask. So, given the image, this is the output of our system for a new body pose. This is what happened at test time, and when we train, we assume that we are given a video of a person, and for each frame on that video, we know what is the right key point arrangement, and we know what is the image. So we can, at training time, we can compare the image that we get out of the system with the ground truth. So we can train the system by minimizing the loss, any reasonable type of loss. So here we use perceptual loss, so-called. It's not super important that we use that particular loss. Anyway, we compare the two images, it gives us some loss, and we backpropagate through the whole system. And so if there is a mismatch between the predicted image and the ground truth image, we can adjust the parameters of the convolutional network, and we can adjust the parameters of the texture. So this is very important that we backprop not only into ConvNet, but we also backprop into the texture stack. So the convolutional network and the textures, they are trained together simultaneously using the same optimization process. Okay? We also predict the mask, and we also compare it with ground truth mask, and this is also used to update the network parameters. There's a separate loss for that. So this is the model. Once again, it's created per person for a given person, and it's trained from a bunch of images of that person from which we know the mask and for which we know the key point positions. So that at test time, we can take this network and we can take these textures, take a new key point arrangement, and recreate a new image of that person. This is the model. Okay, now, so just an example. This is so this system needs good initialization, otherwise it won't converge something good. So we pre-initialize the network to mimic the predictions of the dense pulse system. This is like some small but important detail. Without it, it won't work. So this is what happens after initialization. On the top you see the textures after the initialization for a particular person. On the bottom are the body part coordinate prediction given by the network. You see they're quite coarse. For example, if you look at the hands, they're like very blobby. Once the system converges, the textures become much crisper, much sharper, and the body part predictions also become much more accurate. Okay. So let me show you some result. So this is Igor, part of one of the team members. This in the middle is the video that the system has not seen during training. And admittedly, it's maybe 30, maybe actually even less, maybe 10 degrees off from the video that it has seen, but it's also a new sort of type of motion that the system hasn't seen during training. So on the right, on the left is the skeleton that was extracted from the ground truth video. So the system gets to see the skeleton, and then on the right is the result of the system. Okay, and you see it's not perfect, especially like the head is not perfect, the wrist is not perfect. We have this disappearing watch effect, the patriarch effect, and we also can see that nevertheless there is like some resemblance. Okay, this is in this case we sort of freeze the motion, take the new pose of figure, and change the viewpoints artificially. And here we compare it with, I'll show it again, we compare it with the vid-to-vid system, the NVIDIA system, which has quite a bit more artifacts in this case. So once the vid-to-vid system is using pure convnet, our system uses this decomposition into texture and geometry, where geometry is convolutional, texture is sort of classical, just an image. And this is like, I guess, the last comparison. Again, we see plenty of artifacts, but somehow, these artifacts are perceived as some image artifacts, not something creepy. What's worse is the hand. Hands are a big problem for our system here. Okay. This is, so the previous results were obtained by ample amount of data, like maybe 6 videos of maybe a few thousand frames. Here we train a system for a new person from a single video, okay, that you see on the left. And the system is pre-initialized maybe with Igor, maybe with someone else, I don't remember, but then sort of we initialize the system, we reinitialize the texture, and then we fine-tune for a new person. This is the results that we get. This is like avatars seen from different viewpoints. This is the classical avatar by the authors of the data set. So it's body mesh plus texture in roughly the same key points, and you see like the pros and cons of the approaches. Like the face, the head is probably more realistic in our case. The hands are probably more realistic in their case. So it has its pros and cons compared to the classical approach at the moment. This is one more comparison. Okay. And this is maybe, this is the last result for this part. This was created from just a raw YouTube video. Admittedly, it was cherry-picked. We tried a bunch of YouTube videos. Not all of them worked. This is the one where it worked, sort of. Again, we see some strong artifacts, like on the top right. The hand is once again killing sort of us. This crab-like palm. But for some poses, we get something reasonable result if you look at it at sort of low resolution. This is where we are with that kind of system. Let me just sort of wrap up this part. So we use sort of the power of large generative convnet with millions of parameters to fit the diversity of the, what it needs to generate. Because the body in different poses from different viewpoints looks very, very different. And this is a very complex data manifold to learn, and we use like those millions of parameters to fit this manifold. But on the other hand, we regularize this learning process by decomposing texture and geometry. So that sort of we inject the knowledge that the same body part when we look at it from different viewpoints, have roughly the same color. Okay, this is the idea from classical computer graphics from 70s, the texture maps, and we keep using it here, and it helps us to regularize to avoid some of the artifacts. We can fine-tune this system from one person to another person, use like an avatar created one person to initialize the avatar for another person before learning, but still our systems are, our avatars are per person, and it still can produce some very unhuman-like avatars, artifacts like these palms, or maybe sometimes on the head, we get the pattern which looks nothing like a hand, right? So in some sense it's explainable because the system is trained from a limited number of images, which doesn't capture all the appearance, all the types of, all kinds of views of a hand because of its diversity. So it's explainable that sometimes we get something which doesn't look like a hand. Okay, so how can we solve this? How can we improve on top of that? There is a very simple idea. Okay, we can, when we want to ensure that our system gets something which is human-like, we need to give it some prior knowledge of what humans look like. Not necessarily this particular human, but humans as a general. Okay? So we need some process which trains our avatar, even if it's created for a single person. We need to inject the knowledge about humans in general. And the way we can do it is we can show the system, a large number of videos of humans. So here, in the upcoming part, we will discuss a system trained on an excellent data set of videos downloaded and prepared from YouTube by the Oxford group. It contains, I think, 109 to 160,000 videos, a massive amount of data, and it sort of captures how humans look like. It mostly captures heads, so in this part of the talk I will discuss talking heads model. And the idea is that we will use all these videos of different people and then fine-tune. So we call this stage meta-learning when we show the system all kind of these videos, and then once we do this meta-learning, we then take a small number of views of a new person and fine-tune and learn a new task of mapping the key points of that person to images. This will be a very small fine-tuning process after this huge pre-training meta-learning process. So let me show you what the system can do straight away. So in this case, the avatar, the talking head, was created from 8 views. The views are shown on the top, and then the system was trained on these 8 views to map the key points of the head into the views that you see on the right. So you get like quite photorealistic talking head system. Okay, and you can get these key points, for example, by running the key point tracker on another video. So you can make the person to drive its own avatar, and the new avatar will have a different background, different clothing, different viewpoints potentially. So we can rotate this. Okay, so this is the example where we create an avatar from a bunch of photos taken frontally, and we render this avatar from a new viewpoint, which the system hasn't seen for this particular person, but it used the general knowledge about humans to do this rotation. Okay, so how is it possible? Let me first discuss the meta-learning stage, what happens when we show the system videos of different people. So the architecture has 3 parts: the embedder, the generator, and the discriminator. And the embedder takes a bunch of views, a bunch of frames from the video. It processes each frame, takes input this frame as an input and maps it to a vector. Then it takes another frame. Usually we take like 4 or 8 frames, and we process them through the embedder, and we get a bunch of vectors, and we average those vectors, and this averaged vector is supposed to encapsulate the pose-independent information about this person, about its background, about its clothing. It's in our implementation, it's 512-dimensional vector. Then the generator is what we'll be using at test time or at fine-tuning time. And the generator, the task with the generator is to map the landmarks into a person. So we take a different frame. At each learning episode, we take a different frame of the video, we extract the key points, and we put these key points into the generator, and the generator spits out the image. Okay. What is called synthesized here. And this generation process is affected by the person embedding vector computed by the embedder. And the mechanism that we use is a very popular mechanism these days, adaptive instance normalization, where after each convolution operation, the channels are first normalized and then reweighted by the weights which are computed out of this embedding vector. Okay. And this reweighting ensures that the textures, the patterns are person-specific, that it generates this particular person. Okay, we compare the synthesized image with the new image, with the ground truth image, which we have for this video, right? In several ways. We use the content loss, like per pixel loss and perceptual loss, for those of you who know this. And then we also use a separate network, a discriminator network. Of course, we do GANs. Who doesn't? And this discriminator network uses the mechanism of projection discriminator, which recently became popular. So this discriminator has its own embedding for each video, which it uses to ensure that the resulting frames are not only realistic, but also typical for this particular video. Okay, so this discriminator, it also has different behavior. It also adapts for different videos using these embeddings. Okay, so there's this complex loss per pixel, perceptual, and then the one computed by the discriminator network. Discriminator network usually is trained adversarially to the generator network and the embedder network. So the game here, the adversarial game, is between the generator and the embedder on one hand and the discriminator on the other hand. Okay, and this is trained for days on like bunch of GPUs on lots of videos. And once this is trained for a new person, okay, now let's pretend this is like slight inaccuracy in the slide. Let's pretend this is a new person that the system hasn't seen during training. So for a new person, we have a bunch of images, like these 2 images. We put it into the embedder. The embedder gives us a vector. We average those 2 vectors. Then we take the generator, we condition it on this embedder, and now the generator is able to generate new images of this person for different new key point arrangements. That's the idea. Okay, so after we do this embedding, we can forget about the embedder, and we can sort of generate new views. This is how it's the simplest variance is supposed to work. Now let me give you a quiz. These are some results for this method for 2 people, 3 different variants. In the left case, it's been trained from a single photograph, in the middle from 8 photographs, and the right from 32 photographs. And this person is rendered in from a new viewpoint in a new pose. Okay. Now the quiz is, can you guess these people? Obviously, you definitely know the top one. Most of you, the majority of you, and maybe many of you will know the bottom one. So these are some familiar celebrities. Any guesses? Any wild guesses? I don't have a prize, but I should have had. Okay, this is the right answer. This is the ground truth. Okay, so this is Britney Spears and the actor which from How I Met Your Mother, and who remembers the name? Okay, so the outcome is that we failed, right? So that we synthesize something realistic, but it's not really that particular person. So what do? It turns out that we can actually, a bunch of works appeared simultaneously with our work that did roughly what I have just described, so the time was ripe. And this is where they stopped. And this is the kind of the results that they obtained. They were roughly the same quality as these ones. But we went one step further, fortunately. And this step is fine-tuning. So what we do is we don't stop with those results. When we create a new avatar, we take the images that we have. We do what we have just discussed. But we also say we want to continue a learning process for that particular person using just those few images. Okay, so now we'll do something crazy. We will train tens of millions of parameters on 2 images, 1 image, or 8 images. Okay, but we really start from very good initialization, and we do only a few learning steps, maybe like up to 100 epochs. That's what we do this day. So we initialize the embedder, we put the embedded parameters into the generator. Now we fine-tune the whole parameters in the generator, and we also reinstantiate, reinitialize the discriminator. And at training time, we have a separate loss, which ensures that the embedding and the parameters that the discriminator have, they match. So we can sort of initialize this projecting this discriminator. And so we run GANs with tens of millions parameters in generator, tens of millions parameters on discriminators on a few images. But we do it for a very few steps, and these few steps do magic. Let me show you the magic. So the magic is supposed to start. Okay, so here we fine-tune the one shot example, the 8 shot based on 8 images, and the 32 images, and all of a sudden people become recognizable, right? So they become not perfect, but very, very good, very similar. You can recognize them. So these are some, once again, the comparison. That's what we get from one photograph for that particular person. This is the avatar that we get from 8 photographs. This is the avatar that we get from 32 photographs. Of course, 32 is better than 1, slightly better, but this slightness, if you don't know this person, may look to you the same. If you do know this person, there's a huge difference. You will see that the 32-based image result is much more personalized, much more accurate than the result based on one photograph. Okay, some more results, all based on 8 photographs for lots of celebrities from the holdouts part of the Vox celeb dataset. And then this is the first author of the paper, Igor Zakharov. So this is like a challenging case for us because the system hasn't seen any selfie videos, any photographs. It's only YouTube videos of celebrities. And you see that it's sort of, not perfectly, but sort of generalizes to selfies. So we can create Igor avatar from 16 photographs. This is an avatar from the second author, Sasha. You can compare with the real Sasha. And it's actually working reasonably well at this resolution, right? So if you want to push it to high resolution, then it's much more challenging. That's what we're working on right now. Okay, we can push it further, get some results for historic photographs of Marilyn Monroe, Salvador Dali. Here, one important aspect is that we need to get key points from somewhere, key point tracks, and it's super important to get them from a person who is anatomically similar to the prototype. So to get these decent results, we had to sift through a large number of personalities in the Vox celeb dataset to pick those who are similar to Marilyn Monroe and Salvador Dali, and to transfer their key point tracks to Marilyn or to Salvador. Okay, we don't need to stay in show business. We can do it for Fedor Mikhailovich, for Einstein. Of course, like the hair of Einstein goes, is rendered in a very bizarre way. So hair is one of the most challenging things to model in humans, after brain probably. We can even try it for paintings, and somehow it does give you something reasonable. And if you do it for famous painting, you get lots of hype. That's what happened when we published the results. So we sort of would get like lots of mentions and discussions in popular press of all kind of news outlets, from BBC to NTV, and of different degrees of reasonableness. Maybe the two poles were the Wired, which gave like very nice summary of the work, and the related works to the Sun, which doesn't even mention our names, said some Russian geeks did something horrible which will end the humanity in the way we know it. Okay. So to recap, the avatar part, the both parts of the avatar that I discussed. So I discussed two things: the textured neural avatar, when we regularize the learning by an explicit decomposition of geometry and into geometry and texture. Geometry modeled by ConvNet, textures modeled by an image, and it does regularize and avoid some artifacts. And the second system, the few-shot adversarial learning of avatars, that regularize the learning by priming the system on a huge data set of videos of different people. Both of these sort of works. The second probably works more efficiently, better. We get higher realism. The natural idea is to combine the two and to expand the second system to full body or upper body. In both of these things, both of these instances of this task has significant challenges and hurdles, and that's a part of the future work. Okay, and in the remaining 10 minutes, I will probably switch to the left side of the equation, to the performance capture, and discuss our reason to work on capturing the body key points. Okay. For those of you who are not familiar with the area, it is roughly state-of-the-art discussion, 1 minute discussion of state-of-the-art. Nowadays, our community can track 2D key points quite well. There are just off-the-shelf tools. You download them, you run them. They don't give you perfect results. Sometimes they're jerky, and this jerkiness gives us quite a lot of headache, but generally, it's almost a solved problem, 2D key point tracking. 2D means that it gives you just X and Y, not the depth. Okay? 3D key point tracking, so from a single image, is a very challenging problem which the community is actively working on. It's doing some progress, but it's still a hard task because it's an inherently very ambiguous task. It's very hard to estimate, even for humans, it's very hard to estimate the accurate depth of different key points by looking at a single image. And our initial focus here is to solve an easier problem, is to track 3D key points from multiple cameras, okay, from multiple views. And this is interesting for two reasons. First of all, we can use multi-view setup to track the person, to track the key points. It will do well, but it obviously doesn't fit the bill that I discussed initially, that we want the setup to be simple, easy. So this has its limitation, right? But the second reason why we want this functionality is because we want to capture good ground truth for monocular 3D key point tracking. Because the progress in 3D key point estimation from single image is very severely limited by the availability of good ground truth, because it's not easy to create a diverse and to annotate diverse data set of key points in 3D. You cannot just show any photograph to a person, to an annotator, and ask the annotator to annotate it, the person would not guess it. So we need these multi-view setups. That's the most viable way to get ground truth to train a monocular system. That's why, part of the reason why we focused on it initially. It also turned out to be quite under-researched problem, so there were quite some, I would say, some low-hanging fruits that we picked up, and that's what we'll discuss now. So the problem formulation is the following. We have N cameras, or like C cameras, with known camera parameters, and they are synchronized. Synchronization, by the way, is another big issue, which is not so easy to obtain as you would think, because people move actually quite fast. So synchronization is very hard to achieve, but we assume that we have it. And so we know the projection parameters, and our goal is to predict the 3D key points of a person based on multiple views. Okay, our approach is based on triangulation. Triangulation is a very simple kind of inverse problem. So let me remind you what it is. So assume you have, like, say, two cameras, for simplicity, two cameras, C1 and C2 with known parameters. You have a 3D point X. Then you can project this point onto these two cameras, get the points. And triangulation stands for the inverse problem. When given the projections, you want to recover the 3D point. Okay? So the task is recover the point given its projection on the cameras with known parameters. You can do it in many ways. The simplest way is to say, well, is to use a linear algebra. It's not the best way in terms of accuracy, but it's the easiest way. You go to projective geometry, you describe a point with 4 homogeneous coordinates. You say that each projection defines a ray. Each ray is defined by 2 planes. So you have sort of 4 planes constraining 4 homogeneous points. So it boils down to a bunch of linear equations, homogeneous, which you can solve using SVD. If you have more than 2 cameras, then it's an over-complete system. Then you solve it in a least squares sense. Still, SVD can solve it straightforwardly. Actually, even if you have 2 cameras, then in real life you won't get, yeah, okay, so yeah, it's still, so if you have 2 cameras, it's 4 equations of 4 variables, homogeneous variables, then it's a bit of, yeah, anyway. Now, based on triangulation, you can recover the 3D pose given any 2D key point detector. As I mentioned, 2D key point detection is sort of a solved problem. So you can take a 2D key point detector, you can run it on each of the views. You sort of get the key point positions, and then you triangulate each key point separately, for example, using algebraic triangulation, and you get the 3D pose. Algebraic triangulation, as I discussed, is not the best way, so you probably want to do some outlier. You definitely have to have some outlier detection and rejection process. For example, the Ransack algorithm, which is standard in computer vision, which sort of detects which projections are bad ones and which should be thrown out of this linear system. Okay, and that gives you some result. Now, in this new work, which will be presented at ICCB, we discuss 2 ways to improve this simple triangulation scheme using what we call learnable triangulation. The first model stays close to algebraic triangulation, so we still extract key points using 2D, and sort of we get those 2D key points. And we still solve a bunch of linear equations using SVD to get the pose. The difference is that we weigh those equations using weights predicted by the same network that extract the key points. Okay, so we fine-tune the network to predict not only the key points positions, but also sort of confidences, and we train it end-to-end based on some training data where we have 3D ground truth. Okay, so that's a very simple idea, very straightforward, and still it works quite well. The second scheme, which I still have maybe 2 minutes to discuss, is more sophisticated, slower, but gives you better results. It's based on unprojection system. So key point detectors predict the key points based on heat maps. So as an intermediate result, it produces the heat maps, which are maps for each pixel. So that we get the probability of each pixel containing the particular key point. And the idea is that we can unproject those heat maps into 3D space. And so we voxelize the 3D space around the person. And so for each voxel, we find out by projection what is the probability of the projection of this voxel to contain different key points. Okay, so we get C cameras, and then we unproject those heat maps to get volumes. So we aggregate, so for key points, we sort of aggregate by using sum or max k volumes containing for each voxel the probability of this voxel to be projected onto various viewpoints, and so that this projection has this certain key point. Okay, so we get this bunch of 3D maps, and then we put it into a 3D convolutional network, which processes this bunch of 3D maps and gets us 3D heat maps, out of which we extract 3D key points by the so-called soft-to-argmax operation. Soft-to-argmax means we potentiate, we exponentiate the value at each position, then we take the center of mass of those exponentiated maps. And that gives us the output. So the idea here is that, you clean up and you sort of propagate information between key points using this V2V network, this volumetric network, and it gives you much better results than, for example, key point by key point triangulation, because it, for example, can learn some body prior. Okay, it can learn that this key point should be somewhere between this key point and this key point. And if I just do 3 separate triangulation process, I don't have this body prior, but this V2V network can learn this prior. Okay, so it does give you quite strong improvement. These are the results. The lower is the better. Actually, the state of the art was something like 49 or 47 at the point of publishing. Even accurately implemented run cycle, if we treat it as a baseline, gives you 27.4. It's a good result, but it's slow because you have to run the run cycle multiple times. And then with algebraic implementation, you get 22, which is quite a big improvement compared to the baseline. And then with volumetric aggregation, you get even lower to 20.8. Okay, these are some qualitative results. Yeah, you can see it. So here what you see on the right is sort of pseudo ground truth. So this is the ground truth given by the authors of the data set, and you see it contains quite a lot of mistakes, especially when the person sort of bends. You see that the ground truth goes way off. But even when trained on this particular data set, because data set is large, the learning process regularizes and corrects the error, and you get quite nice results. On the left, in the paper and in the accompanying video, you can see the results also for 2 views. In fact, the volumetric, and it does a reasonable job there. And in fact, the volumetric method can even be generalized to single view, where it gets close to, not quite, but close to state of the art. Okay, so this is about key point tracking. And I need to wrap up. I want to remind you these are like just two sides of equations, the performance capture and rendering. And they're like exponential number of combinations you can explore in both. So this is like a very rich area of research to remind you at the beginning of the topic. It has, when it's solved well, it will have, I believe, very strong impact on people's lives, so it's worth solving. And I probably stop with the photographs once again of the team members who have actually obtained the results I've just presented. Thank you.